Okay, so this is talk about causal inference, and I'll promise to be friendly. And this is joint work with my students, of course, and some collaborators from UT Austin and from Caltech. So 3 parts in this talk. What is causal inference? The second part is a centerpiece is the concept of an intervention or an experiment. So I'll be talking about algorithms of designing those. And then very quickly we will touch the topic of, okay, in some problems you cannot actually intervene, and then there are still some causal techniques you can do. So disclaimer, there are many frameworks for causality, and it's not a particularly friendly field to read about because it splits across many different disciplines, statistics, machine learning, philosophy. Actually, many of the people are in philosophy departments that I will be talking about. So the first one is Granger causality. That relates to if you have time series data. I won't be getting into that at all. The second sort of big landscape is potential outcomes, also called counterfactuals. The Bible there, as far as I know, is a book by Benz and Rubin. I'll give you pointers later. Again, this is not what the causality I will be talking about. And the third style or flavor is called causal graph models, causal graphical models, or PEARLS, structural equation modeling. And this is sort of the model that I will be talking about. There are also other additional variations that we won't be getting into, very briefly touching at the end. So this is a slide I shamelessly stole from Richard Shines from CMU. They have an excellent center there on causal discovery, and they have some short course, even online, that I will link at the end. So people have been thinking about causality forever, and it actually very deeply relates to the problem of interpretability, understanding what your models are trying to do, right? And there was a previous talk by Brian that I really liked about saying, oh, if I have a house and, there's like 3 bathrooms or 4 bathrooms, so I change the number of bathrooms, how does it change the price? But the causal question here is really, if I actually build an extra bathroom, how much will I be able to sell for extra, right? So it's like, if I pick up smoking, how does my chance of getting cancer change? That's kind of questions that relate to the mechanism. So they're actually quite deep, even philosophically. So the 2 frameworks that I described before, potential outcomes and causal graphical models, are here. You see many of the leaders in the area, so we are focusing on the graphical causal models. Perfect. So the first thing to understand is what is a directed graphical model, and that's in the graphical models world, and what is conditional independence, and then I say that's not causal inference, but it's very related to causal inference. So the first step to build is to understand how to learn a directed graphical model. Okay, and before we go there, let's ask an even more basic question. So I'm, an academic, so, instead of putting code, I'll put some very basic math questions down. So let's say that you just have observation data here, just a little table that says I have a bunch of people, and I define heavy smoker, the variable S, in a very specific way. Smokes more than 1 pack per day for more than 10 years or something. And I define the C, the lung cancer variable, again specifically, got lung cancer before 60, etc. So I have an observational data set that somebody gave me from, let's say, 100 people or something with the 0, 1. It's important here that I have no time, okay? So there is no temporal component when they picked up smoking, stuff like that. So I'm ignoring all that, just observational data in this simple form. And the first question we ask ourselves is, okay, I look at this data and I want to check, is there any dependency between the variable S and the variable C, okay? How do you go about checking if 2 random variables are independent? That's like statistics 0, and many people do statistics these days without even knowing probability theory, which is very scary, by the way, to me. But, so the first thing someone will tell you is I'll just take the correlation, right? So I'll just take these 2, the first column, I'll subtract the mean, I'll get a new vector, subtract the mean for the second one, take the dot product of these 2 vectors, and if it's 0 or very small, I will say that these are independent, okay? That's a reasonable answer, but it's not actually totally correct, because as you know, uncorrelated means independent only if the variables are Gaussian, and these are categorical, they're 0, 1, so they're definitely not Gaussian. So the correct way to check independence is you take this table, And you would like to think of the joint probability mass function, okay? So the joint PDF. So the joint PDF here is simply saying, so here is my model for how this data was generated now. There was a monkey up in the sky, and the monkey had this table that I call the joint PDF, and it selects one of those 4 little squares. For example, you see that C equals 0, S equals 0. I think I have a laser pointer here, but I probably shouldn't be using it. So C equals 0, S equals 0 corresponds to this little square, and that happens with 30% chance. So the monkey is going to choose one of those 4 things, and then that realizes S equals 0, C equals 0. And every row in my data is independently, okay, so that's the model. So now, if I just take this data and I compute what statisticians call a contingency table, I'm going to approximate the joint PDF here. I will just count how many 0, 0 I see, how many 0, 1 I see, etc. Okay. Then I marginalize this. So I marginalize across columns, for example. So I add the people who smoke and the people who didn't smoke. And I will see that I have 50% smokers, 50% non-smokers in this data set. So that's the marginal. The bottom blue thing is the marginal for smoking. And if I marginalize in the other direction, it's the marginal for cancer. And now, if these 2 variables were independent, then it means that this table would be produced by the product of these scalars. In matrix language, this matrix would be rank 1, right? So I want to check, the way I check independence is I actually see how well this matrix is approximated by multiplying these 2 marginals. So for example, for the 0, 0 point, cancer equals 0, smoking equals 0, I would be multiplying 0.5 with 0.4, I will find 0.2, but the actual answer is 30%, therefore it doesn't look independent. So the chi-square, Pearson chi-square test for independence that statisticians do computes how closely this marginal, the product of marginals is to the true distribution. So let's say that we have a machine of checking independence, standard statistics. Now, the next step is what is conditional independence. Okay, conditional independence, for example, here we have, A points to B points to C. It means that A and C are conditional independent, conditioned on B, right? So basically the point is this corresponds to a factorization of this joint distribution as I have written here. And a directed graphical model, when we say a direct graphical model, we mean basically a set of distributions. And these are all distributions that factorize according to this graph. Okay, so when we say a directed graphical model, we just mean all the distributions in the world that have these independencies. Okay, and given data, let's say that there's an algorithm that's the PC algorithm it's called, and we can find all conditional independencies from observational data under some reasonable assumptions. Great. So then, learning a directed graphical model, which is a problem that has been studied a lot, is learning all conditional independencies, but that's not learning causality. But as I said, it's the first step to learning causality. So let's understand what causality now is. So we say smoking causes cancer, okay? And we just want to see from this data if smoking causes cancer. So we have to define what causes means very carefully. So here is what I mean smoking causes cancer. So we will say that S has a right arrow to C if the universe is created as follows. So this would be one potential universe that could be generating the data. There is a monkey up in the sky. The monkey first flips a coin and decides if someone is a smoker or not smoker with 50% chance, okay? After the monkey has decided if it's smoker or non-smoker, looks at the conditional distribution, which is a little table here, and if the person is a smoker, so S equals 1, it looks at this little right column here and makes cancer equals 0 with 10 out of 50 and cancer equals 1 with 40 out of 50. So that's a mechanism that could be generating the data. My goal when I ask the causal question is my data generated by such a mechanism as opposed to another one that I will explain in a second. So in Pearl's language, which is called structural equation, the cancer variable, C, is a deterministic function f of the smoking variable and some exogenous randomness E, and this exogenous randomness E, and that's crucial, is independent from the smoking variable. This simply means that in order for this monkey to flip its coins, to sample from these tables, it needs some random dice, and this random dice is what E provides. This is some independent randomness, independent of anything else in the universe, okay? So the structural equations of Pearl can be seen simply as a monkey flipping coins in this. So that's what we mean smoking causes cancer, okay? But maybe there's another universe where cancer causes smoking. Okay, wait, what does that mean? So how could cancer cause smoking? Well, maybe I am born with some gene, okay, and that gene will give me cancer by 60 for sure, let's say, just to keep it simple, and also makes me like nicotine, okay? And maybe it's not even a gene, maybe it's some quantum meta gene, some other thing that we don't even know exists right now, right? Okay, so how would the world work in that case? Well, let's see. So there would be a monkey that would first flip the coin for the cancer gene, the cancer variable, and observe that the numbers, I have calculated the numbers so that everything is the same as before. You would see the same joint probability distribution at the end of the day. So the monkey, when I'm born, decides to give me cancer or not with 60-40, and then looks at the conditional table and decides if I will like nicotine and be a smoker or not, okay? And as you can see, the way this is made, if you are going to get cancer, you actually like nicotine more, right? So the way that, if you look at these numbers, okay? So this is a possible universe that could be generating my data, all right? And in the Pearl's language, it means that the smoking variable is a deterministic function of the cancer variable and some exogenous randomness that is independent from cancer. Okay, great. So what is the task of causal inference? The task is from observational data, tell me if the data came from universe 1, where smoking causes cancer, or if the data came from universe 2, where cancer causes smoking, or there could be another universe where there is no causal relationship between the two. Maybe the monkey just samples from a joint PDF and assigns both of them, and there's no causal relationship between the two. Practically speaking, when a person is a smoker, they care about, hey, if I quit smoking, will that affect my chance of cancer, right? That's what they care about. If they have some gene, they're going to get cancer anyway, then you shouldn't tell them, you should tell them just keep on smoking, right? So that's the question, right? Seriously. So it's all about messing with the data to understand the mechanisms about causality, right? Okay. So the question is, how can we tell? If you know anything about probability, you know that a joint PDF on two random variables can be factorized in both ways, right? So that's the bad news here, is that any PDF on two random variables can be interpreted by both universes, okay? So that's the punchline. If I just have two random variables and I just have observational data, it is impossible to find the true causal direction from observational data because any PDF factorizes as P of C times P of S given C, and in the other direction too, okay? So, the main message that as I guess is in Pearl's work is that instead of observational data, we need to do interventions. And we will talk about what that means in a second. Interestingly, as a side comment, there is a beautiful and rich theory. If you have more than two variables, if you have three, for example, just from factorizations, just from observational data, there are some causal relations you actually can learn, okay? And there is an algorithm for that you can use. So, but just for two, it's clear that if you don't make extra assumptions, you cannot do anything. Great. So, interventions. What does it mean to do an intervention? So here comes the main message of this talk. We force people to smoke, okay? So, wait a minute, let's think about that for a second. So a bunch of people are going to come to my study, and I will intervene on the variable S, all right? Intervene on the variable S means I say, hello, welcome, let me flip a coin. I flip a coin with 50% chance you're in the smoking group, please have a cigarette. And otherwise, I will assign you to the group, or you can do whatever you want, right? So the easier example is, I flip a coin, I force you to smoke, 50%, I force you not to smoke. Let's just take that. So now, what does the monkey, let's think of the monkey now, right? If the data was coming from the first universe, okay, then the monkey is flipping its first coin and says, okay, this guy's a smoker, but you're intervening, right? So you see this stops it, says, I don't care what the monkey does, I'm intervening with the process that generates the data. So now I'm collecting new data, and now, will I see a difference in this intervened data if the data was coming from universe 1? That's a key question. If you think about it a little bit, it's actually, in this case, you will see exactly the same data. The intervention data you will see is going to have the identical distribution as the one you would see without the intervention. But if your data was coming from the cancer causes smoking world, then you would see a difference. Why? Because the monkey would first flip the coin of cancer, okay? So it would decide who gets cancer. And then the monkey, as you can see in the conditional tables, makes the cancer people want nicotine and makes the other people not want nicotine, right? But I don't care because I'm forcing the smoking variable, right? Therefore, if I'm in the intervention, after I collect the data from the intervention, I will see, in this case, independent. The random variables S and C will be independent. Okay. So that's the central message I want to communicate to you, is that even with quantum genes or some unobservable universe in the world, I could, in principle, check the causal direction if you allowed me to do this intervention, right? Okay, so that's the first message that I want to communicate. The power, the gold standard in causal inference is interventions. Now you may be saying, oh, that's all absurd, right? We would never force people to smoke, right? Or do something as crazy as that. And so this is a fun thing I found yesterday. This is from Dallas Buyers Club, if you know the movie. And the guy has HIV, okay? So he goes to the doctor is looking at him, and he tells her, hey, I have HIV, I read that the FDA has a drug in trial that helps HIV, and I want to buy it, okay? And the doctor tells him, well, that's not how it works. There will be a randomized control trial, you come in the study, and with 50% chance you'll get the drug, otherwise you'll get a placebo. So he's looking, it's actually the moment right there, and he's saying, you're giving dying people sugar pills? Okay? So half of the people have HIV, you're going to give them sugar pills, and they're going to die, right? You know they're going to die, which arguably perhaps is worse than forcing people to smoke. Perhaps. Well, this is a morality discussion we can have later, but it's in the same ballpark of hardcore stuff, and that's every clinical trial we do, right? So designing interventions is a pretty serious business. If you're in a startup and you're just doing A/B tests, you know, you're not killing people, but you know, you may be wasting a couple of dollars on the way. So still it's an important problem. Okay, so all these problems now become more interesting when you have more than two variables, right? So you have a bunch of genes, for example, and you have some causal structure. So these are typically directed acyclic graphs called DAGs, because we don't believe that the causal structure has cycles. There is also a causal theory with graphs with cycles, but it's more complicated, so let's just stay on DAGs. So this is the true causal directions for the variables, and you want to learn this, right? Okay, the first thing is you collect some observational data, and you basically look at independencies, conditional independencies, and so from observational data you learn basically the graph that's called the skeleton, which is basically going to tell you, oh, I see that there's some correlations here, and there's lack of correlations there, or conditional independencies, but I don't know the directions, because as we said, we cannot learn directions. So this is called the skeleton graph. And after we have done that from observational data, our task is to start designing interventions to learn all these directions of edges, right? Okay. In the first step, actually, we run the PC algorithm, which is like a classical thing in causal inference. As I said, you remember I said if you have more than two variables, there are a few causal directions you may actually learn for free without interventions. These are called immoralities. For example, here, if the causal graph had S1 and S7 causing S2, that would be called an immorality. Apparently, it's called an immorality because the parents of S2, which is S1 and S7, are not married. Okay? So that I guess so. But you would be able to learn these causal directions just from observational data. But other than those, you wouldn't be able to learn much. Okay, so then you choose a set and you intervene. So here I have the green set, the variables S1, S2, and S4. Intervening means you randomize S1, S2, S4, and now you set them to random values, you collect more data back, you run conditional independence tests again, you rerun the PC algorithm, and you're going to learn some directions. Which directions do you learn? Basically, you are going to learn the directions of the edges on the skeleton graph that connect the set you're intervening on with its complement, okay? So you're learning every edge that crosses from intervened variables to non-intervened variables. That's a simple way of thinking about how interventions reveal causal directions to you, okay? So now, you reapply, you say, oh, is there any extra causality directions I can learn? So you use some standard tools and you maybe learn a few more, and then you repeat, you do another intervention experiment. So the key question that in this line of research now is, given a skeleton graph, how many interventions do I need to learn all the directions of all the edges of a graph? And there are three sub-questions. One is I have to decide on the experiments a priori, it means I'm not adaptive. Or you could say, hey, maybe I will be adaptive. I will run an experiment, learn some causal directions, then choose where to intervene based on my previous answer, run another experiment, etc. Right? So that would be an adaptive algorithm. And then you can also allow from some probability of error to a randomized algorithm. So this has been questions that many people have been studying, including in my research group. So in 2014, there was a very cool paper that said that chi is the chromatic number of the skeleton graph. So you color the graph with a proper coloring. So every two adjacent edges have different colors. And then log of the chromatic number is the number of interventions you need to do to learn any causal graph. That was a very nice result. There was an open problem that was, if you can be adaptive, choosing your next experiment or your next intervention based on the previous ones, can you do better? In IPS 2015, we showed that adaptivity does not help in the worst case. And then there have been some other works that say that if you randomize, you can do better, actually. So you can actually draw log n only for the complete graph case. So we have an algorithm that for a general graph right now will produce what we think is the state of the art in the number of interventions needed to learn all the causal directions. And this is an active area of research, so I will talk about it more later, but there are some packages that you can use. Now, the last question in the 3 minutes and 40 seconds I have left is what you can do if you cannot intervene on the variables. Well, you basically make more assumptions, and now you're in a different ball game. And the way you compare is there are some standard data sets where we know the causal direction, for example, smoking and cancer, because we have other knowledge, right? We know about the mechanism. There's another one that is age and blood pressure. We know age causes blood pressure because we understand the mechanism. But if I just give you numbers, you wouldn't be able to tell necessarily. So we have some labeled data sets, and we run different algorithms and see how well they do when we know the causal directions. So, very briefly, I'll tell you two models that are very popular that you can try to use. One is the additive noise models, where you assume that one variable is a deterministic function of the other plus some noise, and the noise is independent from x, critically. So these are called additive models, and they work pretty well, but your variables have to be numerical. They cannot be categorical. And we are developing a new framework that's called entropic causality. We use information theory, and that's, I think, a pretty good framework if you have categorical variables and you want to find causal directions. So, conclusions. Learning causal graphs with interventions is an ongoing field of research. There's some pretty cool papers about it, and I can point you to them. There are also a few packages that are pretty good that I will point you to. Tetrad is a very good thing to start using if you're interested in that. If you have time, so if you have time series data, then there is other tools you can use. A very popular one is called difference in differences, the DID method. So basically there are other tools in addition that you can use if you have time in the game. And additive models and entropic causality models are there if you have only observational data, but you have no time and basically you have to relax your assumptions, and then we have to compare and see how well we are doing based on some datasets. We know the true direction. So that is all, and I will stop here.